In this video, we are going to be looking at thermodynamic processes. We will understand what thermodynamic processes are and how they connect to thermodynamic state. We also get to look at how the properties of the thermodynamic state can cause or affect thermodynamic processes. At the end, we are going to be looking at the mathematical relationship that connects all thermodynamic processes. Now, a thermodynamic process is said to occur when a system undergoes a change from one state to another. Now, let's say we have a state. Let's say this is state 1 of a system. We have another state here. Let's call this state 2. Now, if a system undergoes a change from this state to state 2, we simply say a process has taken place. Now, what then is a thermodynamic state? A state simply defines the condition of a system at a given point in time. It defines the condition of a system at a given point in time. Now, what are the properties that defines the condition of a system at a given point in time? Those properties can be pressure, temperature, volume, entropy, enthalpy, internal energy, and so on. But in this video, we are going to be considering three key properties that are responsible for the state or that can define the condition of a system. Those properties include volume, pressure, and temperature. So for the first state, the pressure here can be labeled as P1, the temperature here can be labeled as T1, and the volume here can be labeled as V1. And for the second state, the pressure here can be labeled as P2, the temperature here can be labeled as T2, likewise the volume as V2. So whenever the pressure of a system increases from its initial pressure to the final pressure, we simply say a process has taken place. For instance, if the pressure of a system is 5 newtons per meter square, and after heat is being applied, the pressure increases to 10 newtons per meter square. In that case, we simply say a process has taken place. Likewise, when the temperature changes from T1 to T2, or the volume changes from V1 to V2, we simply say a process has taken place. Now, the law that connects this entire properties together, or these entire processes together, is what we call the first law of thermodynamics, which states mathematically that the heat supplied to a system is equal to the change in internal energy plus the work done on the system, where the work done itself on the system is simply given as pressure times change in pressure times change in volume, which is simply given as V2 minus V1. V2 being the final volume, V1 being the initial volume. So this is work done formula in thermodynamics, and this is the first law of thermodynamics which governs all processes. Now, there are 5 basic types of processes in thermodynamics. We have the isobaric process, we have the isochoric process, we have the isothermal process, and we have the adiabatic process and the cyclic process. But in this video, we are going to be skipping the cyclic process and we'll talk about the other 4. So let's start with the isobaric process. Now, an isobaric process is simply a process in which the pressure does not change. A process in which the pressure does not change, which simply means that the pressure is constant. So when a system undergoes a change from one state to another state without a change in pressure, such a process is called an isobaric process. Now let's see what that looks like on a PV diagram. So this is our PV diagram. This is our pressure volume diagram. So let's say this is our state 1. Let's define this as our state 1, and let's define this as our state 2. Now you have state 1 for the volume, state 2 for the volume, but then the pressure remains constant across. Now this is the property as state 1, this is the volume as state 1, this is the volume as state 2, but the pressure remains constant. This is P1, this is P2. So you see that there is no change in pressure. This is the pressure line, this is the pressure line, this is the volume line. So this is our first volume V1, this is our second volume V2. So you see the pressure at volume V1 is simply P1, pressure at volume V2 is simply P2. Since the pressure remained the same, then we simply say this process is an isobaric process. Okay, so for an isobaric process, this simply means that P1 is equal to what? P2. It is simply called a constant pressure process. Therefore, mathematically, for an isobaric process, the work done is going to be equal to change in pressure, pressure times change in volume. So it still remains P multiplies V2 minus V1. This still remains work done. Okay, so for the isobaric process, of course, from first law of thermodynamics, if we plug in this equation for work done here, we are simply going to have that the heat supplied for an isobaric process remains the internal energy, change in internal energy, plus P multiplies V2 minus V1, keeping in mind that P2 is equal to P1, and that can simply be what? P. So for an isobaric process, pressure is simply constant. Now, let's move to the next type of process, which is isochoric process. An isochoric process is simply a constant volume process. In this process, it simply means that volume is constant. So when a system undergoes a change from one state to another, the volume of the system does not increase, even though the pressure on the system is increasing. Now, picture a glass of water. No matter how you increase the pressure on the glass, the volume of that water does not increase. The volume of the water is equal to the volume of the glass. Now, an increase in pressure can actually result to what? Damaging the glass itself, right? But the volume of the glass or the volume of the water does not increase. Such a process is said to be an isochoric process, in which, regardless of the amount of heat or the amount of pressure applied on the system, the volume remains the same. So let's illustrate this using a PV diagram. So on a PV diagram, these are volume, these are pressure. Once again, the first state for volume. In this case now, volume is not changing, so volume remains constant. So these are volume, but then pressure can increase. This is P1, pressure can increase. This is P2, but then if the volume cuts across something like this, this is now V1 and this is V2. So this process is called a constant volume process. So this is what the PV diagram looks like. This process, in which the initial volume is equal to the final volume, is simply called a constant volume process. For this, V2 equals V1. So if the initial volume is equal to the final volume, it simply means that there is no work done for a constant volume process. Why? Simply because we know that mathematically, in thermodynamics, work done is simply pressure multiplied by change in volume, V2 minus V1. So if V2 is equal to V1, if you plug that into this equation, this simply means that work done is going to be equal to P into V2 is same thing as V1. So you have V1 minus V1, and that gives us 0. So automatically, work done is equal to 0. So for a constant volume process, work done is simply equal to 0. And if you plug that into the first law of thermodynamics, you're going to now find that the heat supplied at constant volume is simply what? Equal to the change in internal energy. So the higher the heat, the higher the internal energy, and vice versa. Okay, so next we'll talk about the isothermal process. Now, an isothermal process is a constant temperature process. That simply means that regardless of the amount of heat supplied on a system or the increase in pressure that causes a change of a system from one state to another, the temperature remains the same. Now, this can be seen when you're cooking using your gas cooker. If you lit up your gas cooker to a certain temperature, that temperature is what supplies heat to whatever you're cooking. Let's say you're boiling water. So far you maintain a certain temperature, the water or whatever you're cooking boils according to that temperature. So the only thing that is actually being affected is the internal energy within the system, within what you're boiling, that is being affected. Temperature remains constant. If temperature remains constant, the internal energy of the system continues to change. So whenever you have an isothermal process, this simply means that the only thing that is being affected is the internal energy. So the increase in temperature changes or result into an increase in internal energy. Decrease in temperature results into a decrease in internal energy. And if the temperature remains the same, also the internal energy of the system remains the same. So for a constant temperature process, let's illustrate that with the PV diagram. So this is our PV diagram. Okay. So for a constant temperature process, it simply means that The only thing that is being affecting the system is an external body for a constant temperature process. The external body in this case is when you're using your gas cooker to what? Cook or maybe boil water. The gas cooker becomes an external body supplying heat to the system. So this means that the flow diagram is going to look something like this, because an external body is supplying what? Heat to the system. So this is called a constant temperature process. For this process, it simply means that the initial temperature T2 is equal to what? The final temperature, and therefore the change in temperature dt is going to be what? Equal to 0, because change in temperature simply means T2 minus T1, and if T2 is equal to T1, that simply means T2 minus T1 becomes T2 minus T2 or T1 minus T1, which simply gives us 0. Now, like I mentioned earlier, the temperature is being supplied by an external factor, and that temperature that is being supplied by an external factor affects only the internal energy. So this simply means that if dt is equal to 0, that also means that the U, or change in our internal energy, is also going to be what? Equal to 0, because the internal energy responds according to the what? External factor that is being, or external temperature that is being supplied to the system. So from the first law of thermodynamics, for a constant temperature process, our change in U becomes what? 0. Therefore, we are going to have that work done is equal to what? Oh, sorry, heat supplied is equal to the work done on the system. So for a constant temperature process, which is called isothermal process, the heat supplied is equal to the work done and vice versa. Meanwhile, the internal energy equals 0, because temperature is change in temperature is 0. Finally, we talk about the adiabatic process. An adiabatic process is a process that do not supply heat and mass to the environment. It is simply a process that do not supply heat or mass from the system to the environment. A good example can be seen in your thermoflask or in your thermos plus. Now, a thermoflask is simply a device that is used to trap heat, hot water for a very long period of time without exchanging that heat to the surrounding. So that's a good example of what an adiabatic process is. A process that do not interact or exchange heat from the system to the surrounding is simply called an adiabatic process. So this simply means for an adiabatic process, heat is what? Conserved. And if heat is conserved, it simply means that heat is equal to 0 for an adiabatic process. Now, on a PV diagram, you have something like this. This is volume, and this is pressure. So once again, an adiabatic process, the entire energy is within. The entire energy is within. For that reason, you have the flow process to look like this, the PV diagram to look like this. Okay, so this is an adiabatic process, and for this process, I mentioned earlier that the heat supplied is simply what? Equal to 0, because heat is conserved. Heat is not being exchanged to the environment, therefore heat is conserved. And if it is 0, then that simply means that from the first law of thermodynamics, 0 is equal to change in U plus W. So you're going to have 0 equals change in U plus W. And therefore, change in internal energy is going to be what? Negative work done. So this simply means that the higher the internal energy, or the higher the change in internal energy, the lower the work done, and vice versa. So in general, an isobaric process is simply a constant pressure process. An isochoric process is a constant volume process. An isothermal process is a constant temperature process. And an adiabatic process is simply a process where heat is not being exchanged to the surrounding. And the mathematical relationship that governs them has been duly explained here using the first law of thermodynamics. When it is isobaric, the work done remains P multiplies V2 minus V1, and the heat supplied is simply given as this change in internal energy plus P into V2 minus V1. For an isochoric process, there is no work done because volume is conserved. And if volume is constant, then our work done is simply what? 0. So we only have heat supplied, be it equal to the change in internal energy for an isochoric process. For an isothermal process, we have that our work done is equal to what? Heat supplied to the system, simply because the internal energy responds to changes within the temperature or caused by the temperature. For that reason, change in temperature equals 0, as much as change in internal energy also is going to be 0. So we have our heat supply to be equal to work. Energy is conserved. And finally, for the adiabatic process, there is no heat exchange between the system and the surrounding. In that case, the Q is simply taken as what? 0. And Q is taken as 0. And of course, this simply means that the internal energy is equal to negative work done and vice versa. So that's it for this video. In the next video, we're going to be employing everything we've learned here to start solving problems that has to do with isobaric, isothermal, isochoric, and adiabatic processes. I'm sure you want to be a part of that video, so do well to hit the subscribe button and turn on your bell notification so you don't miss out on that video when it drops. I will see you in the next video. Cheers.